In this video, we're going to learn more about our derivatives and find one of the most useful things about derivatives. We can use them to figure out what the graph of a function looks like and to find its relative extrema, which are the high or low points of the graph. So let's start with the definition. We're going to let f be defined in an interval. And we're going to let x1 and x2 be points in the interval. Then we say that f is increasing on the interval. If f of x1 is less than f of x2 for all x1 less than x2 in the interval. And we have a similar definition for the function being decreasing. We say f is decreasing on the interval if f of x1 is greater than f of x2 for all x1 less than x2 in the interval. And we say the function is constant on the interval if f of x1 equals f of x2 for all x1 and x2 in the interval. So all of these definitions that we just wrote down are honestly a little bit technical. But what it's actually saying is the graph of the function will go up from left to right if the function is increasing. The graph will go down from left to right if it's a decreasing function. And the graph will be completely flat horizontal if it's a constant function. So just for example, let me draw just a random graph here. We would say that this function here is increasing from all the way on the left side till right around here. Then it's constant. And then it's decreasing. Switches again to increasing and switches back to decreasing. So whenever it's going up, it's increasing. When it goes down, it's decreasing. And when it's flat, it's constant. So now let's just take a look at part of this graph. Let's look at this increasing portion here. Take a look at what happens for all of my tangent lines on an increasing part of the graph. What can we say about the slopes of all of those tangent lines? Well, if your function's increasing, the slope of the tangent lines are all going to be positive. Similar idea when it's decreasing. If I draw some bits of tangent lines here, all of these tangent lines have slopes which are negative. So we know all about how to find the slope of the tangent line. That uses our derivative. And so we have a theorem that ties our derivative into increasing and decreasing functions. Here's our theorem. Let f be continuous on the interval, closed interval AB, and differentiable on the open interval AB. Then we have three things that are true. If the derivative of f is positive for every x in the open interval AB, then f is increasing on the open interval AB. And I do want to say a little warning here. A lot of textbooks will say that this is increasing on the open interval AB, but there are some textbooks out there that call it a closed interval AB. In particular, the book that we're using in our class, if you're a current student of mine, they like to use these closed intervals. So if you're working on homework, you're going to need to use closed intervals to have our homework system mark it as correct. I personally like it with open intervals. It makes more sense to me to have it increasing on an open interval rather than increasing at the endpoints, because I don't know what it means to be increasing at an endpoint. So I tend to use the open intervals like this in my answers, but depending on your book, you might have to use this to get the answers correct on a homework system. So just be very careful with that. That's part of our theorem. If the derivative is positive, we're increasing. Part B, if the derivative is negative, for every x in the open interval AB, then f is decreasing on AB. And again, you might need to use closed brackets depending on your particular homework system. And part C is for where the function is constant. If the derivative is exactly equal to 0 for every x in AB, then f is constant on AB, or AB in closed brackets. So this tells us that we can figure out if the graph of the function is going up or down or staying flat just by looking at the derivative of the function. And so let's do our first example using the derivative to find where our function's increasing or decreasing. So find the intervals where f of x is increasing or decreasing. For the function f of x equals x squared minus 4x plus 3. So we know that the function is going to increase when the derivative is positive, and it decreases when the derivative is negative. So let's start by finding our derivative. Using just our power rule, I have a 2x and minus 4. So now to figure out where this is positive or where it's negative, what I personally like to do is first find where it's equal to 0. So I would add 4 to the other side and then divide by 2. So I know that my function is, my derivative is equal to 0 at x equals 2, but I need to find out where it's positive and where it's negative. So then what I do is I make a number line. Here's my number line. I'm going to label it with the derivative so I know what I'm using. And I'm going to put the values I found where it was equal to 0. And now I can think of this as dividing this number line into two pieces. I'm going to check a value inside of my derivative on this side and check a value inside the derivative on that side to figure out if it's positive or negative on that part of the number line. So you should choose numbers that are easy to work with. I would choose 0 over on the left. F prime of 0, if I look at my derivative here, if I plug a 0 into it, I'm going to get -4. It's negative, and that means that we are decreasing over on this side. Now I just need any number over on this right side, so I'll choose 3. If I plug a 3 into my derivative, I'm going to get 6 minus 4, which is positive. So I'm increasing on that side. Now notice, yes, I could have actually evaluated that 6 minus 4, it's 2, but I tend to not actually evaluate it. All we care about at this point is it positive or is it negative? So sometimes you might have very complicated looking derivatives. You don't have to calculate it all the way out. You just need to find out if it's positive or negative. So now we have all of the info we need. We can write where it's increasing and where it's decreasing. Our function is increasing starting at 2 and going to infinity. And it's decreasing from -infinity to 2. And again, depending on the homework system, you might have to use brackets like this to get marked as the correct answer, though I personally do not like that because to me it doesn't make sense to say it's increasing and decreasing at the point 2. It's neither at that particular point, which is why I use the parentheses, and I'm going to continue just using parentheses for the rest of the videos. Just wanted to point that out in case your homework system requires brackets, you'll know what to do. All right, so we found where we're increasing and where we're decreasing just by looking at our derivative. Let's do another example. Find where the function is increasing or decreasing. And our function is 3x to the 4th plus 4x to the 3rd minus 12x squared plus 2. So if we're going to find where this is increasing or decreasing, we need to find the derivative first. Finding the derivative of this function just uses the power rule. I'm going to get 12x to the 3rd plus 12x squared minus 24x when I take my derivative. And then remember, the way I like to do it is set it equal to 0, find every place it's equal to 0 first, and then check pieces of the number line. So I'm going to set this equal to 0 and solve this equation. And I can solve that by factoring. First, I'll pull out the greatest common factor of 12x, which leaves an x squared, an x, and a minus 2. And then I can factor this piece here even further. So when I factor this piece even further, I get an x plus 2 and an x minus 1. So now I know all of the values that make this 0 are 0, 1, and -2 when I just take each piece and set them equal to 0. So now I can test what happens to my derivative in each piece of my number line. We're going to have more values to check this time because I had more places where the derivative was 0. So put the values you found on the number line, make sure they're in order, and notice that this divides my number line into 4 different pieces. I'm going to need to check something in each of these pieces, and we should try to pick values that are sort of easy to work with. So I'd probably use -3 on that side, -1 here. I guess we kind of have to use 1/2. That's about as easy it's going to get there. And probably 2 on that side. Now, to figure out if it's positive or negative, the easiest place to figure that out is where you have your derivative already factored. So let's look at this -3. If I plug a -3 into my factored derivative here, the 12x will be negative. -3 plus 2 is negative. -3 minus 1 is negative. So I have negative times negative times negative, so it's going to be negative. I guess I can just write a minus sign to indicate that. Now let's see what happens with -1. If I plug a -1 in here, it's negative. -1 into x plus 2 gives me something positive, and -1 minus 1 is negative. Negative times negative is positive. Now let's try 1/2. It would be positive here, but 1/2 minus 1 is negative. Positive, positive, negative gives me negative. And when I plug in the 2, I get positive, positive, positive. All those positives multiplied together is positive. So this means I'm decreasing everywhere I had a negative, and I'm increasing everywhere I have a positive. So now it's just a matter of writing these as intervals. So let's do increasing first. I'm increasing between -2 and 0. And then again, starting at 1 until infinity. And then I'm decreasing in this first chunk, that's -infinity to -2. And I decrease again between 0 and 1. And there we go. We found where the function was increasing or decreasing by looking at the derivative. So whether something is increasing or decreasing tells you quite a bit about the graph, but it doesn't tell you everything. It just tells you if it's going up or going down. But there's a lot of different ways to go up or down. For instance, a curve that looks like this is increasing, but a curve that looks like this is also increasing. They're both going up from left to right, but they're curved a little bit differently. The way that this curves, we call that concavity. This one is what we call concave up, and this one is concave down. Similarly, we can decrease 2 different ways. This guy is decreasing, but this guy is also decreasing. They're both going down from left to right. This first one is concave up, and the second one is concave down. So notice that both of these concave up pieces, they look kind of like a parabola when we put them together, like this. So I say concave up is like a cup. It makes a curve that's cup-shaped. Concave down, if I put those 2 different graphs together, looks like this. Concave down is like a frown. So there's your dumb little poem for remembering it. Concave up is like a cup. Concave down is like a frown. And we can figure out the concavity of our graph by looking at the second derivative. Theorem. If the second derivative is positive for every x in an open interval, then f is concave up, which I usually abbreviate as CCU. I don't really know why, it's just the way I do it. but it's concave up on that interval. And if our second derivative happens to be negative for every x in an open interval, then f is concave down, which I use CCD on that interval. So we were able to figure out where the function's increasing or decreasing by looking at the first derivative, and now we'll be able to figure out if it's concave up or concave down by looking at the second derivative. Now before we do that, I want to give us one more definition for something called an inflection point. A point where a function f changes concavity is called an inflection point. So that means that the function is going to change from concave up to concave down, or from concave down to concave up. And the way an inflection point often looks is something like this point right here. I switched from being concave up to concave down at that point. So it's where it changes the way it's curving. Let's do an example where we're going to find increasing, decreasing, concave up, and concave down intervals, as well as any inflection points. Find the intervals where f is increasing, decreasing, concave up, concave down, and find any inflection points. And our function is going to be x to the third minus 3x squared plus 1. So let's start with the derivative, because if we find the derivative, we can find where it's increasing or decreasing. Starting with our derivative, I get 3x squared minus 6x. I want to first find where this is equal to 0, and then I can check where it's increasing or decreasing. So I'm going to factor. I have 3x times an x minus 2. So this is equal to 0 when x is 0 or 2. So I can put those on a number line. Here's 0, here's 2. This is my first derivative. And I'm going to check some values. I'll check -1, 1, and 3. If I plug -1 into this factored derivative, I get a negative times a negative, which is positive. If I plug +1 in, I get positive times negative, which is negative. And if I plug a +3 in, I get positive times positive, which is positive. So I know that I'm increasing on the two outer subintervals. That's -infinity to 0 and 2 to infinity. And I'm decreasing on that middle subinterval, 0 to 2. So we've already done part of the problem. We found increasing and decreasing. Now I need to find where it's concave up or concave down and find inflection points. But I'm going to have to find my second derivative to do that. So our first derivative, before we factored it, was 3x squared minus 6x. My second derivative would then be a 6x minus 6. And to figure out where it's concave up or concave down, we're going to do something just like we did with the increasing and decreasing. We're going to find where this is equal to 0 and then use a number line to check if it's positive or negative. So let's set it equal to 0, and again, I'm going to factor this. Factor out a 6, and I have an x minus 1. We know this is 0 when x equals 1. So I'm going to make another number line. This one I'm going to label with my second derivative. And I only have 1 point on it, x equals 1. I need to check stuff on both sides, so I'll use 0 and 2. If I plug a 0 into this second derivative, I get 6 times negative 1, which is negative. If I plug a 2 in, I would get 6 times 1, which is positive. Now we just have to remember what negative and positive mean with the second derivative. When it's negative, you're concave down. Positive is concave up. So I'm concave up on the interval 1 to infinity, and I'm concave down from negative infinity to 1. And remember, to find an inflection point, we need to find where our graph changes concavity. And we can see it changes at x equals 1. That's where we switch from being concave down to concave up. So our inflection point occurs when x equals 1. If I want to find the y-coordinate of that inflection point, we have to plug that 1 back into the original equation. So I would have 1 to the third minus 3 times 1 squared plus 1. So this is 1 minus 3 plus 1, which is negative 1. So my inflection point is the point 1, negative 1. All right, and that's all there is to it. And you can see we're going to get a lot of info about what the graph of these functions look like. And in fact, by the end of this video, we're going to start doing one graph by using all of this information. Now, if there is an inflection point, it occurs where our second derivative equals 0 or is undefined. So when you're trying to find your concavity, you should find where your second derivative is 0 or where it's undefined first, and then check using the number line. I didn't bother checking where it's undefined on the last example because we had a polynomial, so it was defined everywhere. Let's do a definition again. A function f has a relative maximum. That's also sometimes called a local maximum at x0 if there is an open interval containing x0 on which f of x0 is the largest value. And similarly, f has a relative or local minimum if there is an open interval containing that x0 on which f of x0 is the smallest value. So these definitions here, I feel, are a little unnecessarily wordy. What this is saying is that you have a relative maximum if it's the tallest point, just looking at points near it. And it's a relative minimum if it's the shortest point among all the points near it. It makes more sense when you see a graph. So let me just graph some random function here to show you what I mean. All right, so when I look at this, I see that I have a relative maximum at this point, because when I look really close to it, that point is the tallest point. I also have a relative maximum here, because again, looking at points close to it, it's the tallest point. And I have one more relative maximum here. It's the tallest point among the points close to it. So in orange, we have all of our relative maxima. For the minima, you look at points that are lower than all points near it. So I would have one here, here, and down here. These are our relative minima. Now notice that, well, a really good example is look at this relative maximum here. It's not the tallest point on the entire graph. That's this guy over here. But it's okay, it's still a relative maximum because when you look just in a little neighborhood close to it, it's the tallest one. That's all it means to be a relative maximum, is that when you look just close by, it's the tallest point. And same for relative minimums. So we're going to be able to find these relative extrema, which are relative maxima or relative minima, by using our derivative. Here's a quick definition. A critical point is a point in the domain of our function such that the derivative of the function at that point is equal to 0 or is undefined. And we do say if f prime at that point is 0, we sometimes call that critical point a stationary point. That's not a universal language there, but some textbooks like to call them that to make sure you distinguish between the derivative being 0 or the derivative being undefined. All textbooks agree that both of those situations are critical points, just some of them also give this extra name of stationary point to those that have a derivative equal to 0. So why do we care about these critical points? Well, because if there happens to be a relative maximum or relative minimum, it's going to occur at one of these critical points. That's our theorem. If the function has a relative extrema, so again, that's a relative max or a relative min, at x0, then x equals x0 is a critical point. So notice this does not say that every single critical point will give you a relative max or a relative min. It just says if you have a relative max or min, it's going to happen at a critical point. So if we're trying to find a maximum or minimum, we need to find all the critical points first because those are our candidates for being maxima or minima. Let's do an example where we find some critical points. So find the x-coordinates of all critical points of f of x equals 3x to the 5/3 minus 15x to the 2/3. So I know from my definition that a critical point is a point where my derivative equals 0 or is undefined. So we should find the derivative before we do anything else. Using my power rule, I get that this derivative is, well, 3 times 5/3 is 5. X, my new power is going to be 2/3. And then the 15 times 2/3 would be a 10. And I would have x to the negative 1/3 as the new power. And we're going to find where this is equal to 0 or undefined. So let's first try to rewrite this a little bit better. Let's factor out our greatest common factor. That would be 5x to the negative 1/3. When I factor that out, I'm going to have an x minus 2 left behind. And then I can rewrite that x to the negative 1/3 in the denominator. So I get that my derivative is equal to 5 times x minus 2 over x to the 1/3 power. So now we can find where this is equal to 0 or undefined. We'll do the undefined first. Where is this derivative undefined? Well, it's going to be undefined when we divide by 0. That happens when x is equal to 0. Now, to find where our derivative is equal to 0, we just set the whole thing equal to 0 and solve. So if I multiply by the denominator on both sides, I have this. So really, it's just the numerator equals 0. And this is 0 when x is equal to 2. So I have my x-coordinates of my critical points. I have x equals 0 and x equals 2. And this x equals 2, we can also classify as a stationary point. Both x equals 0 and x equals 2 are critical points. And x equals 2 we can classify further as a stationary point because the derivative was equal to 0 there. So, first derivative test is a test we need to learn. It says if our first derivative is greater than 0 to the left of a critical point x0, and the derivative is less than 0 to the right of the critical point x0, then x0 is a relative maximum. So let's think about that real quick. This is saying if my function changes from increasing to decreasing at that critical point. And that makes sense. If we're going up and then switching to going down, we're going to have a maximum. That makes sense. We also have, if the first derivative is less than 0 to the left of x0, and the first derivative is greater than 0 to the right, then x0 is a relative minimum. And again, this makes sense. This is saying if I'm decreasing and then I switch to increasing. So we're going down and switch to going up, there's going to be a point at the bottom that's our minimum. Now, if I have neither of these situations showing up, then that critical point just does not happen to be a maximum or a minimum. It would be neither. Let's do an example using this first derivative test. So using a previous example, remember we had that the derivative of our function was equal to, I had 5 times x minus 2 over x to the 1/3. And we had found critical points of 0 and 2. So now I can figure out where we're increasing or decreasing, and then we can use that first derivative test to determine which of these is a maximum and which is a minimum, or neither. So let's check -1, 1, and 3. If I plug a -1 in, the top is going to be positive times negative, and the bottom is going to be negative. So I would have negative over negative, which is positive. If I plug a 1 in, my denominator is positive. My numerator would be a positive times a negative, so it would be negative. And if I plug a 3 in, my numerator is positive and so is my denominator, so I get positive. So this means that this point 0, using my first derivative test, my function's changing from increasing to decreasing. So this has to be a relative maximum. And over here, my function is changing from decreasing to increasing. So this would have to be a relative minimum. That's how you use the first derivative test to determine if something is a max or a min. But we also have a second derivative test, which sometimes is easier to use. The second derivative test says if the derivative is equal to 0 and the second derivative is positive, then x0 is a relative minimum. And if our derivative equals 0 and our second derivative is negative, then x0 is a relative maximum. And then if our derivative equals 0 and the second derivative equals 0, then it's inconclusive. We can't tell. It's possible that x0 could be a max or it could be a min. We don't know. You would have to use the first derivative test instead to figure that out. So let's do an example where we find the relative extrema using the second derivative test. Find the x-coordinates of the relative extrema of the function 3x to the fifth minus 5x to the third. Well, first, I have to find my critical points, because we know if there are relative extrema, they're going to occur at our critical points. So take your derivative to get 15x to the fourth minus 15x squared. And notice this is a polynomial, so it's never going to be undefined. So I just need to find where this is equal to 0. I'm going to factor. And I'm going to keep factoring until it's fully factored to get all of my critical values. My critical values are 0, 1, and -1, which is found by setting each of these pieces equal to 0. So I have 3 possible candidates for relative maxima and minima. Now, I said we were going to use the second derivative test to see if these are maxima or minima. So let's find our second derivative. Now, when finding the second derivative, I would suggest that you probably just take the derivative from this part here rather than the factored version, because then you don't have to use a product rule. So if I use my power rule here, I would get 60x to the third minus 30x, which if I then factor it just to make it a little easier to work with, I will have 30x times an x squared minus 1. Sorry, 2x squared minus 1. There's my second derivative. So now we're going to take our critical values, plug them into the second derivative to see if we get something positive or negative. That will tell us if we have a max or a min. So let's start with the critical value x equals 0. For x equals 0, my second derivative would be equal to 30 times 0 times 2 times 0 squared minus 1, and this is equal to 0. This is inconclusive. That does not mean that x equals 0 is not a maximum or a minimum. It just means that I don't know. Using the second derivative test, we don't know what this point is. We'll have to use the first derivative test on that one, and we'll check it after we check these other guys. Let's try x equals 1. If I plug x equals 1 into the second derivative, 30 times 1 is positive. 2 times 1 squared minus 1 is positive. So I get something greater than 0. No matter what it is, all I know is it's greater than 0, and that's fine. Second derivative being positive means that this is a relative minimum. Now, if I use x equals -1, I would get 30 times -1 times 2 times -1 squared minus 1. So I get negative times positive, the whole thing is negative, and we have a maximum using our second derivative test. So what I know so far is x equals 1 is a relative minimum, and x equals -1 was a relative maximum. And we don't know about 0. To figure out what 0 is, we're going to have to use that first derivative test. So let's remember what our first derivative looked like. In factored form, our first derivative looked like 15x squared times x plus 1 times x minus 1. And if I look on the number line, well, here's 0. My other values were -1 and 1. I don't really care what's going on everywhere. I need to know what's happening here and here. So I can figure out if 0 is a max or a min. So if we just check values in those two subintervals, let's use -1/2 and +1/2. Let's see what happens. If I plug -1/2 in, well, the 15x squared will be positive. -1/2 plus 1 is positive, and this guy would be negative. So the whole thing is negative. Now, if I plug in +1/2, I'd get positive, positive, negative. The whole thing is negative. So is this a max or is this a min? Well, it's neither. I'm decreasing before 0 and I continue decreasing after 0. So my only relative extrema are the two we already found. This is neither. I could not tell from the second derivative test. That was inconclusive. But I can tell with the first derivative test that this is neither a max nor a min. All right, to finish this video up, we're going to do a rough sketch of a polynomial using all the information we've learned in this video about increasing, decreasing, concavity, all of that. So let's sketch y equals x to the third minus 3x plus 2, including all intercepts, relative extrema, and inflection points. So let's start by finding all of the intercepts. That doesn't use calculus. Let's just get that out of the way. Let's find our y-intercept first. Your y-intercept is when x is equal to 0. So I get y equals 2. So 0, 2 is my y-intercept. For my x-intercept, I need y to equal 0. To solve that, we would need to factor. And you will get x plus 2 times x minus 1 squared. So I get x-intercepts of -2 and 1. So I have -2, 0, and 1, 0 as my x-intercepts. And now we're ready to do the calculus part. So before I start my calculus, let me just write down what we have so far. So we'll have it ready to go on our graph. So I have the point 0, 2, the point -2, 0, and the point 1, 0. Those will all be on my graph when I get to it. Now let's find where our function is increasing or decreasing, because we'll need that information to graph. So remember, our equation was y equals x to the third minus 3x plus 2. Let's find the derivative. Using my power rule, I get 3x squared minus 3. Now this is defined everywhere, so I just need to find where it's equal to 0 for my critical points. I can factor out a 3, and I can continue factoring to get an x minus 1 and x plus 1. So x equals 1 and -1, those are my candidates for being relative maxima or minima. Now I'm going to put it on a number line so we can figure out where we're increasing or decreasing. Here's my first derivative number line. I guess I should just call it y prime. And we'll check -2, 0, and 2. And again, the easiest place to check is your factored version. When I plug in -2, I would get negative times negative, which is positive. When I plug in 0, I get negative times positive, which is negative. And when I plug in 2, positive times positive is positive. So this tells me, my first derivative test tells me this guy is a maximum and this guy is a minimum. I already know the y coordinate of this point. It's 0, we already had that. But I should plug this -1 into my original function to figure out what that point is. So if I plug my -1 into the original function, I get that we have y equals 4. So these were all my intercepts. I now also know that this one, 1, 0, is equal to a min. And I have another point in my graph, -1, 4, which is a max. And let's write down where this function is increasing or decreasing. We are increasing from -infinity to -1, and again from 1 to infinity. And we're decreasing between -1 and 1. So I have all this information up here that will eventually be graphed, but now we need to find inflection points and concavity to make sure we have the most accurate graph possible. So let us rewrite what our derivative was. We had 3x squared minus 3. So my second derivative is 6x. I'm going to use that second derivative to find inflection points and our concavity. My second derivative is always defined. We have to find where it's equal to 0. It's equal to 0 when x is 0. This is my possible inflection point. We just have to check the concavity. So looking at my second derivative number line, we can check -1 and +1. If I plug -1 in, I get something negative. If I plug +1 in, I get something positive. So my x equals 0 is an inflection point. And we can write down where we're concave up and concave down. Concave up from 0 to infinity, concave down, -infinity to 0. And now we're ready to sketch this graph. All right, so sketches don't have to be perfect, but we do have a lot of information we can use to make this fairly accurate. What we should do first is put all of the points that we know on this graph. So I have a point at 0, 2, a point at -2, 0, a point at 1, 0, and a point at -1, +4. And we know that this -1, +4 is a maximum, and this point here, 1, 0, is a minimum. Now we can use the other information to sketch. What I know is that I'm going to start by increasing. I'm going to increase all the way until I reach x equals -1. So I'm increasing this whole time until I reach this point. Now we have to look at our concavity. Am I concave up or am I concave down? Well, I'm going to be concave down until I reach 0. So I'm starting down here somewhere. I'm increasing and concave down until I reach that point at the top. Now that I've reached this point at -1, I'm going to switch to decreasing until I get to x equals 1. And I'm still concave down until I reach x equals 0. Once I reach x equals 0, though, I switch to concave up. So I've changed how I'm curving. I hit my minimum value. And now that I've reached x equals 1, I switch to increasing. And I'm still concave up. And that's my rough sketch of what this looks like. The next video is going to include more and more complicated functions using this technique for graphing. And you're going to find that you can actually graph some pretty complicated functions just using the derivatives pretty simply. So that was a lot of info to digest in here. I hope you come back for the next video where we continue with the same discussion, but just graphing more complicated functions. If you have questions, feel free to drop them below. If you're a current student of mine, you can also ask in office hours or through email. And I'll see you for our next video, which is all about graphing with calculus.